tied in together with the definitions of derivatives and linear approximation, there's another definition kind of hiding in the background, and that is of differentials. So if we start with a differentiable function y equals f of x on an interval that contains a, and we let the x coordinate change from a to a plus delta x, we find that the y values also change. Let me show you on our picture real quick. This is the same picture we had from linear approximation, but it works. So a is this distance from 0 to a, and delta x is this distance. So we go from a to a plus delta x, which gets us over here. What we find is that the y values change from f of a to f of a plus delta x. And we can approximate that, well, let me just put that. Find that the y values, the output values, also change from f of a to f of a plus delta x. Okay, so what we can do is we can kind of tweak that a little bit. So we say let f be a differentiable function on an interval containing x. So we're going to switch it from a's to x, let it be a variable. A small change in x, a very small change in x, is denoted by the differential dx. So when you think about the definition of derivatives that we've been seeing for a long time, we've been seeing dy over dx. Dx always stood for a small change in x. That's what it means. Right? So in other words, let me just bring back the picture really quickly. I let these two values get very close together, right? I make it, instead of being a large delta x, I make it be a little teeny tiny dx. Right? It's called an infinitesimal. So I'm letting them get infinitely close to each other. So the corresponding change in f is approximated by the differential dy equals f prime of x dx. So in other words, this bit right here, which is delta y, right? Delta y is f of x plus delta x, take away f of x. This is discrete. And let me just show it to you on the picture. Delta y is right here. Right? Now it's written differently when we were doing linear approximations, but it's f of x plus delta x, or f of x plus dx, minus f of x. Right? That's what they're saying. So they're kind of using different letters, but it's still true. Right? And it's discrete because you're going over and up, and that's it. Right? So that f of x plus dx minus f of x is approximately close enough-ish to dy, which is equal to f prime of x dx. This is for continuous distributions. And think about this. You've kind of already seen this because we've seen the definition. Right? There's the Bernoulli notation, there's the Leibniz notation. F prime of x is a small change in y over a small change in x, right? Because it's a slope of a line, and this is based off of the slope that we know from algebra, change in y over change in x. So if I just multiply both sides by dx, I'll have it. So I'll have f prime of y, or excuse me, sorry, f prime of x, sorry, f prime of x dx is equal to dy, right? If you manipulate the Leibniz notation that we knew from earlier, you get the same thing. Great, so that means that we can find dy, and I have to tell you that differentials are not difficult because we've already worked with derivatives so much, and they get used all the time. There's actually an entire classes devoted to these, to equations with these, called differential equations. So what they are equations that involve derivatives rather than equations that involve variables. And you can take multiple classes on that. I particularly enjoy those classes. I like differential equations. I find it fun. All right, so we are going to find the express the relationship between a small change in x and the corresponding change in y in the form dy equals f prime of x dx. Now, it sounds so intimidating, but it's actually really simple. All it means, essentially, is find the derivative and then multiply. So, f prime of x, which we all know is dy over dx, right, is equal to, and now we have to be able to take the derivative of this, but we learned how to do that in an earlier chapter. We would use chain rule. So use chain rule. So you'd make it 2 times the tangent of x times the derivative of tangent, which is secant squared of x. So therefore, dy is equal to 2 tangent of x secant squared of x dx. And you're done. That's it. That's all there is to it. Right? Okay, so for this one, g prime of x, which is dy over dx, is equal to, now for this one we're going to need quotient rule. All right, so 4 minus x goes in front, 4 minus x squared is in the denominator. In the numerator, I'm going to take the derivative of x plus 4, which is 1, because that's a line, so its slope is 1. And then I'll leave the x plus 4 alone, and I'll multiply by the derivative of the denominator, which is negative 1. So that would be 4 minus x plus, because minus a minus is plus, x plus 4 over 4 minus x quantity squared. The x's cancel, so we're left with 8 over 4 minus x squared. So that's dy dx. And that means dy is equal to 8 over 4 minus x squared dx. And we're going to use this little trick a lot in Chapter 5 when we're doing integration. So this is a little trick that's going to come back to us. All right. So let's do a small problem that involves differentials so you can see an application of differentials. And it's going to be very similar to the linear approximation applications because, well, they're intimately tied together. So we're going to use differentials to approximate the change in the volume of a right circular cone of fixed height 4 meters when its radius increases from 3 meters to 3.05 meters. All right, so let me draw a cone shape here. I should have had a cone pre-drawn on the notes, but that's all right. Okay, so we have a cone, right? It's got a back to it right there, and the radius is right here, and the height is right here, right? The height is fixed down the center, and that height of that cone is set at 4 meters. It's never changing. All right, now if I look up the volume, well, let me real quick notice, they want us to use differentials to approximate the change. Use differentials to approximate the change in volume. In other words, they want dV, right? The change in volume, but with differentials. So a small change in volume. Okay, so I need a volume function for starters. All right, volume for a right circular cone is 1/3 pi r squared h. Now that's a little bit of an issue for us because that is actually 2 variables. That's r and h being used right there. So we don't really have an h that's changing, but we do have a radius that's increasing. So I want to be able to use the fact that my height is 4 no matter what, right here. So I'm going to put that in right there. So I'm going to say that this is equal to 4/3 pi r squared, and I'll just make a little note because the height is 4 is constant. Never changing for this particular problem. Okay, so now remember from just a page ago, right, dy is approximately f prime of x dx. Now, we don't have x and y, so we better figure it out. So if we look at our volume function, v of r, right? So for us, the y is v. So dv would be equal to f prime, so v prime, because v is our function, v prime of r dr. All right, so I need to find v prime. V prime of r would be, bring the 2 down, so that'd be 8/3 pi r, and this would be equal to dv dr. Therefore, dv is equal to 8/3 pi r dr. All right, so we've got our change in, so this will be the approximate change in volume for a change in radius, for a small change in radius. That's what we're finding right there. Okay, but now I have a specifics that I'm looking for. Sorry, that was off screen. I have specific values that I'm looking for. I want to know what's happening from my particular values. So I had a starting value of, let's see, right here. So there's my starter. My start is 3. So I'll make a note of that down here. And we're going to end up at 3.05, right here, right there. So that's our ending value. All right, so I'm just gonna make a note, end at r equals 3.05. Oh, these aren't centimeters, I'm sorry, these are meters. There's no C there, sorry. So that's an M. All right, and from there I can determine my delta R. My delta R is the difference between those two. So change in R is equal to, remember how it goes, x minus a for the basic. So for us it's going to be, in other words, let me put it this way, it's end minus start. That's the way that works. So for us it's going to be 3.05 take away 3, which is 0.05 meter. That's our delta R. All right, so then I've got my delta R. I've got 8/3 pi. I'm going to need my, I have my R value. That's 3, right? So I'm just going to be able to put this in for delta R. So delta V, so change in volume is approximately V prime at R times delta R, or times dr, right? That's this formula right here. Change in V, which is dV. So dV is equal to this, so delta V is going to be similar to that. So I just need V prime of R and dr. dr I'm going to approximate with 0.05. And of course, I have my V prime value, or my V prime just figured out right here. So I'm going to use that V prime to substitute in my value. So I want V prime of 3. As a matter of fact, I'll just make a note of it right here. So V prime of 3 and V prime of 3 is equal to 8/3 pi times 3, which would be 8 pi. So they asked us to use differentials to approximate the change in volume. So I'm getting the change in volume right here, dV, which is V prime of R, dr. I'm approximating, so I'm saying, here, let me put it this way. dV is approximately delta V, right? They're very similar to each other. So I'm using, there, I just rewrote it. I think that'll make it clear. So dV is what we wrote above, V prime of R dr. And so what we're doing is we're approximating with delta V, which is V prime of R delta R. So we'll say that's 8 pi times the delta R, which is 0.05. Right? dr is technically minuscule, so delta R is an approximation. And then that would get us 0.4 because 8 times 5 is 40, so it's 0.4 pi. And then this is the change in volume, right? So this is meters cubed. All right, so quickly recap. We have a volume function, too many variables. We use the constant to make one variable, a singleton. Then we remembered that if we're going to use differentials, we use this basic differential formula right here, and we rewrote it with our particular variables. So v is our function and our y value, and then dr, because r is our radius, which is our x value. Then we found v prime, which is dv over dr, which means dv is equal to 8/3 pi r dr. We have a starting value and an ending value, so we use that to find delta r, which is an approximation for dr. And then we also found v prime of 3, and that got us 8 pi. So that way we could take the same formula we have up here, and we could kind of rewrite it down here. Well, it's actually this formula right here. And then we rewrote it. dv equals 8 pi times delta r. That's approximately 8 pi times delta r, which was that value.